After class, you can pick up your exam. All right. Do you have any questions?
I do believe it was a homework for 14. One of them I didn't accept.
Which one is it?
It was the one with the altitude of the triangle one.
Okay. What about it?
I didn't quite understand it right. I did finally get solved it, though it took a lot of trying and a lot of speculation on my part.
Okay. So and tell me the exercise so I can look it up here.
I,
What problem is it?
I believe it was question 4 or 5.
From homework
14.
14. Okay. So let's see. Check this one. Okay, so 4 or 5. This
That's
one?
the one.
Okay, let's see. So the altitude of the triangle is increasing at a rate of 3 centimeters per minute. So they're telling you the speed at which it's increasing. While the area of the triangle is increasing at a rate of 3 square centimeters per minute. Okay. At what rate is the base of the triangle changing when the altitude is 8 centimeters and the area is 99 square centimeters? So the first thing that you should do is draw a little picture. Let's see. So this is a homework question. We're talking about, this is question 4 from homework 14. So homework 14, question 4. Okay. Share this. Okay. So again, I'm gonna draw a little picture of the problem, right? So in the question, we have a triangle, right? And they talk about the altitude, which is the height of the triangle, and then there is also mention of the base, which is what we need to find somehow. So we have a triangle. We don't know whether triangle is a right triangle or not, so we should not do that. Okay. So this is 14, question 4. So I'm just gonna draw any triangle here. Okay. This is a triangle, and then it has a height. Let's call it H, and then it has a base. Let's call it B. Okay. So in the problem, they say, this triangle is getting bigger. Okay, because we're being told that the area is increasing at a rate of 3 centimeters per minute, 3 square centimeters per minute, and the altitude is increasing at 3 centimeters per minute. So you can imagine that this is a triangle that is open somehow. I don't know what's going on. Like somebody blowing a balloon that is a triangular shape or something. Or maybe you're analyzing a particle moving and then you want to figure out the relative distance from this point between these two vertices, and then that forms a triangle. I don't know. There is also a problem in the homework about two chips that they start at a certain position.
Oh, yeah.
One move this way, another one this way, and you actually need to consider a triangle that is growing. Okay, so you can imagine that this could be a similar situation. The point is that we have certain quantities here. So what are the quantities involved in this problem? So certainly we have the height, right? So we have the height, we have B, which is the base, and then we have A, which is the area. And we're being told that these things are growing, so all of these are functions of time. Okay? And T here is time. So these are the quantities in question. So then what's the data that we're given? I'm trying to follow the steps that we discussed for this type of problem. So we're being told that the altitude increases at a rate of 3 centimeters per minute. So that's dH dt. So that's 3 centimeters per minute. And we are also being told that the area increases at 3 square centimeters per minute. So that's dA dt. That's 3 square centimeters per minute. Do you understand this? Yes?
Yes.
Okay, so this is a triangle that's growing, and this is the information, and this is set, this is telling you more or less the speed at which this is happening. This is how fast this thing is growing, and as this happens, then the area also, of course, the triangle gets bigger, then the area increases. Okay, so the next step is that we need to relate the quantities. And in this case, there is an obvious way to relate the quantities. What is it? How do we relate the quantities?
V equals.
There's no V here.
No, that's wrong.
There is a triangle. What's the area of a triangle? What's the formula for the area of a triangle?
A equals pi r squared. No, that's wrong.
It's 1/2 base times height, right? We're talking about triangle. There's no circle here. So it's 1/2 the base times the height. Yes?
Yes.
So we have our quantities related, and then we need to take derivative to relate the rates. Okay, so dA dt. Now notice that here, what do we need to do when we take derivative? What do we need to do here?
Plug in.
Product rule. About half of you in the exam, there was a little question that you need to find a second derivative. About half of you were not doing product rule there. So I don't know. That was a product of two functions. If you see a product, what do you need to do when you take the derivative? Product rule. Half of you were not doing that. It's you see a product, it's product rule. Okay, so that will be derivative of so 1/2 is a constant. I'm just gonna leave it there. So derivative of the first, that's dB dt times the second plus the first times derivative of the second. Okay. All right, and then what is it that we want to find in this problem? At what rate is the base of the triangle changing when the altitude is 8 centimeters and the area is 99? So we need to find dB dt when h is 8 and the area is 99. Okay, so we are after this guy. And so the question is, do we have everything we need to figure that out? Let's see, we know the ADT, we know H, we don't really need A as of now. And we know the HDT, now we have to figure out B. Now, how do we find B at that point in time? That's when we need the area. We need to come back to the triangle, right? Because we know that the area equals 1/2 base times the height. So, or if you want, you can solve for B here and then write it in terms of the area. But the point is that at this point in time, the area is 99, the height is 8. We can figure out what the base is at that point in time. Okay? So, when h is 8 and the area is 99, then we have our formula. I'm going to find B. So B is 2a over h, which would be 2 times 99 over 8, which is 99 over 4. Okay, so that's B. Now we have all the numbers. So let's plug them in. So I'm going to call this star. So formula star with the extra data that h is equal to 8, a is equal to 99, and all the stuff that we have from above, we get the following. So dA dt is 3. Then dV dt, that's what we need. So keep it there. Then h is 8. Now B, we know what it is. It's 99 over 4. And dH dt is a 3. Okay. So now everything are numbers, so we just solve for the desired quantity. I'm going to multiply it by 2, so that's a 6. So 6 is going to be equal to 8 times dV dt plus, what is this? 27. And then 297 over 4. 7 plus 2. Okay. So let's move it to the other side and divide by 8. So dV dt is 6 minus 297 over 4 divided by 8, which is, let's see, multiply top and bottom by 4.
6 minus 2. 97 over 4.
Okay, wait. I don't like that this is a negative value.
No, the homework was negative.
Yeah.
Huh?
Yeah, they're all negative.
I read the other one.
So it means that it's getting smaller, the base.
It was supposed to.
That was the answer.
Yeah, that was.
So the base getting, I mean,
Didn't say like all the answers.
so it's going, so this guy is increasing, the area is increasing, but then the base was a negative dBdt means that this is decreasing, right? The quantity B is decreasing.
It's getting skewed.
Yeah, the base. Okay, that's what it is. There it is. Okay, so we have, what is it? 20 multiplied to 1 by 4. So that's 24 minus 297 over 32. And then 297, 24, that's a 3. So that's negative 273 over 32. I just want to put the final answer just to make sure that it will take. And this is centimeters per minute. And then if you have questions, you ask me. But let me just finish it here. So 273 over 32. And maybe this can be simplified, not sure, but let's see. Okay, working. Show you. So we're safe there. So what was confusing for you in this problem? Now that the solution is here, then we can talk about it. So what was the issue?
Well, it was the formula to use it that I kind of couldn't wrap my head around it that well. The decreasing part, since it was it was decreasing, so actually increasing in the negative in the problem.
Yeah, the base is decreasing, but then the height is increasing. So for example, if we look at, let's see.
And
Yeah, this is strange because this is increasing actually at a very fast rate. It's actually, this is decreasing faster than how the height is increasing. The height is only increasing at a speed of 3 centimeters per minute. While this one is decreasing, if you divide this is more than 3. Negative, but it's more than 3 because this times 3 is 96. So it's actually about double. This is decreasing at a speed double than what the height is increasing. But yet, it says that the area is increasing. So, I think it's a little bit weird.
And I think I just overcomplicated.
But the numbers are telling that, so that's not the problem. And anyways, the confusion will have arisen at the end because beforehand we didn't even know that it was going to be a negative number. So the important thing is to be able, for example, to get to this step, right? So it's very important. Then next, to be able to figure out all the quantities that you need in here, which to realize that you are not given the base, but with the given information, you can find it at that point in time. And then you just plug it in and solve it. So at the end is when you realize that it's negative. So that confusion should have not been somewhere in here, okay? It happens at the end, but then the problem is done. So.
Also, I think I just overcomplicated it. When I was trying to get the process down in my notebook, I kept just not seeing it and just keep jumbling it up somewhere.
Okay, I'm not sure what you mean. So remember, I gave you, look, because the thing is, I gave you some steps. The reason you don't have to follow the steps, but the steps is to help you organize your thoughts. Okay? So when you see a problem like this, try to draw a picture that illustrates what's going on. Then make sure that you understand what are the quantities that are being involved. Then write down the written information. Then figure out how to relate the quantity. Usually is via some formula. What formula? Look at your picture. What do you have here? A triangle. You need formulas about a triangle. There are only two possible formulas, perimeter or area. This problem is talking about area, so you look for the area of a triangle. If you don't remember, look it up. You're doing homework, so it's okay to research stuff around and so on. Then make a note, hey, I need to know the formula for the area of a triangle. You put your formula, take derivative, all of these steps were written down in the previous lecture. Take derivative, you have your rates now in place, then try to see if you have everything that you need. So once you get to this point, we didn't even know that we needed to find B at this point. Once you get to this point, you start examining. Okay, what do I have? I have this guy, I want this one. I have this. Okay, I don't have this. I have this one. I need to find B. Take a step back and think about it. How do I find B with the given information? And that's the one that requires a little bit of thinking, and then just to realize that at this point in time there is a triangle that's fixed with this height and with this area, so you can find B. Okay, you do that, and then you're good to go. Do you understand what I said? And this is usually the same thing for all of these type of problems. The same thought process.
I have to look into this again, just to be sure.
Are you sure now? Do you have questions about what we just did?
No, you explained it well. I'm gonna make sure to look over it again, for our future references.
Yeah, try it. Okay, good.
But thank you either way, Mr. Luis.
Okay, thank you. All right, still bothers me that negative, but anyways, I don't like it.
But that was confusing that most of them were
It's decreasing too fast.
about the negative number instead of a positive. It's an increase.
Yeah, there is no way about it. Okay, anyways, it is what it is. Any other questions? Yes.
Section, the first one.
Uh-huh.
The homework.
The same homework?
Yeah, same homework from yesterday, right? This is the same homework we have to do.
Number one?
It's like, I think it's one of those.
This one?
So, I know how to do it, but I keep getting one of the answers that it was 3/4, and I keep getting 12, and I don't understand why.
But are we talking about this one?
It's x equals -1 if y equals -2x plus 3 and dy over dt equals 3.
Oh,
So it's not the same
because
one,
yeah,
but
but it
it's-
is the
yeah.
same idea.
Yeah.
Okay, so in this case, here they want you to find dy dt when x is equal to -1. And now here, the thing is that there are two quantities here, x and y. We already have the relationship among these quantities. And then we need to find dy dt when x is -1 and dx dt is -4.
Actually, the video actually was a really good eye opener for that one. The video,
Okay.
it showed.
Yeah, so almost every question, not every question, but some questions have this little link. You click it and you watch the video. But the point is, here you just take the derivative and then, make sure that you use chain rule, okay? And increase differentiation. And then when you take the derivative, you're gonna get dy dt. Over here, you're gonna have 2x times dx dt. Do you see that? Let me write it the board so we can all see it. So we have y is equal to x squared plus 4. Take the derivative, so that means dy dt is 2x times dx dt plus 0. So of course, it doesn't matter. And now plug in what you need. So what do we have? So we're given x and we're given dx dt. So dy dt is 2 times -1 times
-4.
-4. So we get 8. Yes? Did you do that?
I did that, but I got the answer, but the answer when I put on jump to answer, it gave me 3/4.
Did it mark you wrong the question?
Yeah. And I'm
This
like,
question, not another
not
question.
that question. It was another question in that same one. When you get similar question, another question appeared, and the answer was 3/4, and I'm like, why?
That's strange. Do you mind if I would you mind if I pull up your information here?
Yeah, sure.
Okay. Just want to see. Joshua, right?
Yeah.
14.
Oh, it's not-
No, it's okay.
No, it was like when I clicked on read.
Okay, yeah, you have done
question,
this
I
4
got-
times. Okay.
Yeah. It was that one. I put 12/1 because I thought it was asking me for that, but the answer was 3/4, and I'm like,
So the derivative, what's dy dt here? So dy dt here is -4x times dx dt, right?
Mhm.
So when you plug in, what do we get? You put a -1 here and a 3. So it's -4 times -1 times 3.
The 3's on 12.
So 12, right?
yeah.
I don't know, wait. Oh, we need, no, because here is
Yeah,
different.
it's-
Here they're asking for dx dt and they give you dy dt. So it's on different side. So they are asking for this, and they give you this. So the one that I just did, they were asking for dy dt. This one is asking for dx dt. So you need to divide. So dx dt is 3/4 because you need to divide. I mean, you have to see what they ask you.
Yeah.
Okay. So again, you have this, plug in the given information, and then you will see what you need to do, where you divide, multiply, whatever it is. Okay, good. How about Friday's discussion? Do you have any questions about L'Hopital's rule? Computing limits, indeterminate. Let's see, who can tell me the 7 indeterminate forms?
0/0.
Okay.
Infinity over infinity.
0/0. Yes?
Infinity over infinity.
Infinity over infinity.
0 times infinity.
Good. So help each other. 0 times infinity. You need to know this, otherwise when you see a limit, you need to be able to recognize if you have an indeterminate form or not. Because this is what tells you whether you need to do something or not.
Infinity minus infinity is it's all the way at the end.
Okay. And there's a reason why I put it at the end, because this one you deal with that on its own.
Infinity and plus infinity?
Okay, 1 to the infinity.
Infinity to 0.
What is it?
Infinity to 0.
Infinity to the 0th power, yes?
0 to
0,
0.
0 to the 0. Good. Anything else that comes up, you can figure it out by just looking at it. Like infinity plus infinity, well, that's just infinity. Okay? Infinity times 1, okay, that's just infinity as well. Or infinity to the 1, that's 1. That's infinity. Right? So, there are some situations that you can just figure it out. Or infinity to the infinity, well, that's infinity. And that kind of stuff. What's infinity to the negative infinity? What is this? If you get this type of situation in the limit, what is this? This is 0. Good. Why is it 0?
This is 1 over infinity to infinity.
Exactly. Use the stuff that you guys know. This is 1 over infinity to infinity. Remember, when I write these things, these are symbols, but this stands for some expression that goes to infinity in the limit. And this stands for some expression that goes to negative infinity in the limit. Okay? So you can rewrite it in this form, then the bottom will go to infinity, and 1 over infinity is 0. Okay? So the thing is that with this kind of things, you cannot play like this. You cannot decide the answer immediately, so you have to do something. And remember what the idea was. This 2 is done via L'Hopital's rule. Okay? Everybody remembers L'Hopital's rule? All you have to do is, this means that your function, the limit that you're taking is a quotient of two functions, f over g. What L'Hopital's rule says is that when you take this limit, then you can just replace the top by its derivative and the bottom by its derivative. As long as this limit is a 0 over 0 or an infinity over infinity situation. Okay? That's what L'Hopital's rule says. And then if this limit exists, whatever you get, that's the same as this one. So that's with this, you can deal with these two situations all the time. Now, this one, remember, there is a trick that you do to turn into one of these two, and then you use L'Hopital's rule. This trick, there is another trick that we do to turn it into this form, and then once you're here, you use this other trick to go to L'Hopital's rule. And this one is because you're subtracting two expressions, so you either combine them, like if they are fractions, combine them. It's going to reduce to one of these, or factor something out. Okay, and it will reduce to something like this, for example. Okay, and then at the end of the day, everything follows back to L'Hopital's rule. But if you have some of these, you need to do some work before you can use L'Hopital's rule. Okay, so this is like the king of this section, but you need to know the tricks. So look at the notes and look at the lecture that I talked about, because we're gonna do something else completely now. Okay, completely different. Any questions? Okay, good. So if there are no questions, then let's continue. Let's start looking at applications of derivatives. Remember, our purpose is to be able to study functions, so we're gonna begin doing so right now. Make sure that everything is in place. Okay, so our goal is, the reason why we have been studying derivative is so that we can understand functions. And when I say understand function, the goal of the sections that we're going to begin now is I give you a formula and then you will need to produce a picture of that function. Okay, but to be able to do that, we need to take things little by little. And when talking about function, there are some properties that are very important. Among those is the notion of relative and absolute extreme. Okay, where a function has a maximum or a minimum value. We want to know this. Also, this is useful for applications when you want to maximize or optimize some quantities. So we're going to discuss relative extrema. Then we will talk about monotony, when a function is increasing, when a function is decreasing. Then concavity, because if a function is increasing, it means going up. It could do it in two ways. It could do it in this shape, or it can do it in this shape. Both shapes are going up, but they are different. So which one of the two is, okay? So that's the concavity information. This is called concave down, and this is called concave up, okay? So we're gonna talk about that, and then once we have all of this information, then we'll be able to start producing pictures, okay? Graphing functions. So it's gonna take us a couple of lectures. All right, but let's take a step back and start from the beginning. And let me remind you of the notion of relative maximum and minimum, absolute maximum, absolute minimum that you discussed back in college. Okay. All right. So suppose that you have a function. Examples here. So let y equal f of x be a function, and let's say that this function is defined at the point x equals c. So I want to define what it means for f of c to be a relative or local minimum. So sometimes we say relative minimum or local minimum. It's exactly the same thing. So basically, let me just give you a picture. Basically, to be a relative minimum means the following. Imagine that this is your function. Okay, this is your function f, and let's say that this right here is a point c. So to be a relative or a local minimum means that maybe f of c, the value of the function of c is not the lowest value in the entire graph. But if you zoom in around the graph, so if you look at a little piece around the point c, which is this one right here, if you zoom in there, it is the lowest point. That's what it means to be a relative or local minimum. Okay? When you look at the entire graph, there are points that are lower than that value, but around this point, this is the smallest one. In other words, when you have this sort of behavior, we have a local minimum. Do you understand this? That's what I'm gonna write down now mathematically. Okay? And of course, this one up here would be a local maximum, because if you zoom in around this point, this would be the highest point. Okay? But I'm gonna write this down using math. Okay, so I need to talk about zooming in and just restricting ourselves to a piece on the function, and we can do that by just talking about an interval. In other words, how do we define that little square that you see in the picture? Well, that's just an interval I. So f of c is a relative minimum if there is some interval containing the point c for which the value of the function at c is the smallest one. Okay. So f of c is a relative minimum of f if there is an interval I. So that way, I'm talking about that little box that I draw. Okay. If there is an interval I containing c, such that for all x in I, we have the inequality that f of x is greater than or equal than f of c. So to be a relative or local minimum means that on an interval around this point, any value that you pick inside that interval, the output on the function is going to be always greater than or equal than this particular value. Does it make sense? This is where we're saying that this guy is the smallest value inside this interval. Do you understand this? Okay, so that's what it means to be a relative minimum, and then the language that we use is we say that the function has a relative minimum of the actual value is f of c, and the location happens at x equals c. So we say that f has a relative minimum of whatever whatever this number is at x equals c, or sometimes we just say at c. Okay? But remember, x equals c is the location. This is the actual value, the actual minimum value. Okay? The y value. Are you okay with this definition? And then, in the particular case that the interval I can be taken to be the entire domain of the function, then we call this an absolute minimum. In other words, the absolute minimum of a function is the lowest point if it exists. Sometimes it doesn't exist. Like for example, this graph that I draw here, if this keeps going down non-stop, there's no absolute minimum because it goes down to negative infinity. Okay? So if I equals the domain of f, then f of c is called absolute minimum because it's the lowest point on the graph. Because for every x in the domain, so for every input that you can plug in, the output will always be greater than or equal to this particular number. So this is the smallest that you can get. But this cannot always be done. Like for example, here you cannot always find this. Like this graph is not going to have an absolute minimum, but it has a relative one. Okay. All right. Any questions? Now, similarly, we have a definition for relative or an absolute maximum. Okay, it's the same idea. All I have to do is split this inequality. Okay, to have an absolute maximum means that you get the highest point of the graph inside a little interval, and it will be, that's a local. Absolute is the highest point on the entire graph. So f of c is a relative or local maximum of f if. So let me use the same picture. So this guy is the local mean. And then this one up here, we will call it a local max. Okay? So if there is an interval I containing C such that for all x in I, we have that f of x is less than or equal than f of c. In other words, inside this interval, f of c is the highest value that you can get. Okay, this is a way of saying that this is a relative maximum. Relative because it's on an interval. Maybe on the entire function this is not true. Okay, on the entire domain. But on a piece of it, it is true then. It's a relative maximum. And we say that f has a relative maximum of f of c at x equals c. And again, if we can take the interval to be the entire domain, meaning no matter what you plug in, you will always get something less than or equal than f of c. So this is the highest point overall. We call it absolute maximum. So this is the domain. Then f of c is called absolute maximum. Okay, so our goal is to be able to spot this guy. So given a function, like something like this, our goal is to be able to locate the maximum and the minimum values, or at least the relative extreme. Because maximum and minimum, they don't, absolute extrema, they don't always exist. We can see a theorem that tells us that they will always exist if the function is continuous on a closed interval. Okay, that's called the stream value theorem. If you have a continuous function on a closed interval, then it will have a maximum, it will have a minimum. But in general, we usually just talk about relative extreme. So the option here is I give you a formula and you need to find the location of these points. Okay? And that's what we're trying to work towards too. Okay. So again, relative minimum is just whenever you see this little valley thing, then the lowest point, that's what we mean by relative minimum. Relative maximum, when you see a little mountain, the highest point, that's your relative maximum. Okay. All right. So let's do an example. In this case, of course, we don't want to rely on graph. The idea is to do it from the formula, but we don't have the tools yet. So, but it's something that we can graph. So let's sketch the graph of this function. This is a polynomial, and let's identify any relative extrema that we can see. Okay. All right. So remember, how do we graph polynomials? Here, the hard job is already done. The hard job is to try to factor the polynomial, right? So you can get the zeros. In this case, already factored. So we can easily see the zeros, the multiplicity, and the end behavior. So that's all we need to graph the polynomial. So let's produce a picture. And let's identify the extreme. So let's see. We need to write down the zeros. Who can tell me what are the zeros of this polynomial? What are the zeros?
3, 4, and 0.
X equals 0, x equals 3, x equals 4. Yes? So that means that we need to go through 0, has to go through 3, say 1, 2, 3, and through 4. Has to go through here and through here. Okay? Now, what's the end behavior? Remember, the end behavior is given by the leading term. So let's figure out the leading term. So what's the degree of this polynomial?
6.
So 2 plus 3 plus 1. So degree is 6. And what's the leading coefficient? -1. Good. So when you multiply all of this out, this is going to be negative x to the 6 plus all the stuff. Right? If you were to multiply all of these parentheses, that's what you're going to get. And that negative x to the 6, that's the highest degree, so that's the leading term. That determines the end behavior of the function. Because it's an even power, either both ends go up or both ends go down. Because the negative, they're going to go down. Do you understand what I'm saying? Okay. So that means it comes from down here, and we need to finish down here. Okay? And, we have to go through these points. Now let's see how do we do that. So for that, we use multiplicity. What's the multiplicity? When you factor the polynomial, the multiplicity of a 0 is how many times that 0 appears, and that information is encoded in the power of that corresponding factor. For example, 0 comes from x, yes? Now it's to the square, so that means the multiplicity is 2. We say that 0 appears twice, it's a double 0, okay? Then 3 comes from x minus 3. The power is 3, so the multiplicity is 3. And 4 comes from x minus 4. The power is 1, so multiplicity is 1. Why is this important? Even multiplicity, you touch, and then odd multiplicity, you cross. And you cross in the way that the factor looks. If it's multiplicity 1, you cross linear. If it's cubic, you have to do the cubic shape. So with that information, we're good to go. Because we come from down here, we need to hit 0. Now multiplicity is 2, so we touch it. So it needs to come back down. Then at some point here, which after today or maybe next class, we're going to be able to know exactly when this is going to happen. That's the whole point, okay? But at some point here, we need to turn back around because we need to go to 3. So our job today is to find when is this happening. Who is this guy? Okay, what is this turning point right there? And then we need to go through 3 like a cubic. So you do that little thing. And then once again, at some point, we need to come back down. At some point, we need to come back down and go through 4 in a linear way. Okay? If you zoom in, you should see something. It looks very linear. So this is a rough sketch. For example, this is the best that you could do in pre-calculus. You could do better, but then you have to plot a bunch of points if you want to get a better estimate of how the graph looks. But this is the overall shape. And what we're going to learn today, we're going to know precisely when this happens and when this turning up here happens. Okay? And so you will be able to draw more precise pictures, at least for polynomials, after today. Because that was the only unknown, really, that we had from your pre-calculus knowledge. Because this is, what we just did is pre-calculus. The only thing that was missing is when this turning happens. We will find that out today. Okay. So this is our graph. Any questions on the graph? All right. So then now, the job is to identify relative maximum, relative minimum. Let's see. Let's start with the minimum. Do you see any relative minimum in here? Yes. So hopefully everybody is looking at the same thing. Somewhere in here. Agree? So right here we have a relative minimum. Do you see any relative maximum? So somewhere up here, we have our relative max. Again, this is just to have an understanding of what these things are. Any questions? Okay, so now, do you see another one?
Zero.
Good. I was about to miss that. So what is this? Max. So here we have another relative max. Okay. Questions? Okay. Now, okay. So let's see something interesting. So remember, our job really is to try to figure out what these points are from the formula. Okay. You don't want to rely on the graph to do this because what if you get something that you don't know how to graph? You cannot draw a picture to then identify these things. The idea is to find it without using a graph. So let's try to see if we can find something that they have in common. What do all of these guys have in common? Yes? Very good. So remember, if you have a formula, you can always find the derivative, right? Now, what do you know about the derivative of the function at this point? Remember, derivative is, at the point, is the slope. The slope of what? Of tangent line. How does the tangent line looks like in there? So the tangent line is this guy. The tangent line here is this guy. The tangent line here is this guy. So what's the slope at those points? Slope is 0. Slope is 0. The slope is 0. The slope is 0. In other words, at all of these points, we have that the derivative happens to be 0. Remember, derivative gives you the slope. Yes? So, you know, another thing to say is, well, you know, if you're trying to look for these points, then you should probably look for places where the derivative becomes 0. Okay? Let us try to formalize this statement that I just said. Let's do a couple more experiments. Okay? So I'm going to give you some functions. Let's find the places at which the derivative function that we know how to graph, and let's try to see if when we find a maximum or a minimum, we always see this sort of behavior that the slope is equal to 0. Okay? Maybe something else will come up. So that's the idea. So remember, the motivation here is we're trying to see if we can find a common pattern, like a way to figure out these points from the formula without looking at the graph. So far we have said, well, maybe if we look at the zeros of the derivative. Okay? So let's do a couple more examples. Here I have two functions. We know how to graph these functions. Let's find the relative extrema that they have, and then let's find the derivative and let's evaluate it and see what we get. What are we expecting to obtain? According to our discussion above, we're expecting to get a 0. Let's see if this is always the case. Okay? All right. So solution. Let's look at the first one. The first one is absolute value of x. Now we know how this looks like. How does the absolute value looks like? It's a V shape, right? So it's this guy over here. So as the absolute value function, you know, and it goes through 1, 1, negative 1, 1, and so on. Okay. So do you see any relative extrema in here? Where? At x equals 0. Remember, relative extrema is just on the graph, whatever is at the lowest point. If you have it, then it has a relative extrema, right? So there is a relative extrema here. In fact, it happens to be the absolute minimum as well. Okay, so a relative minimum could be an absolute minimum. But in other words, any absolute minimum qualifies as a relative minimum as well. All right, so this right here is a relative minimum. And there is no relative maximum. So we have a relative minimum at x equals 0, right? So what we're trying to figure out is what happens when we find the derivative of the function and we plug in 0. Who can tell me? What is this? Does not exist. Remember, when you have peaks, the derivative doesn't exist. It's undefined, it's not differential. And the way to think about it is you cannot talk about slope here because if you take the left derivative, the slope is going to be negative 1. If you look at the right derivative, the slope is going to be positive 1. So you have two possible slopes. Okay? So remember, absolute value has a peak, so it's not differential here. But this is still a minimum. So that conjecture that we had that the derivative must be 0 doesn't hold anymore. Okay? It could be that the derivative does not exist, but maybe that's the only cases. Okay? And in fact, that's the idea. If you're going to have a relative extrema, then two things could happen. Either the derivative is 0 or is undefined at that point. Okay? So that's the upshot of this discussion. So does not exist because f is not differentiable at 0. So it could be that you have a relative extrema and the derivative is not defined. So let's look at the other function, which was sine. Now, this one, let's just do the interval from 0 to 2 pi, because we know the rest is just copies of it. So sine function, and we want to analyze it on this interval. So we know how this looks, so let's graph it. So here is 2 pi, split in 4. It's pi over 2, pi, 3 pi over 2, and then from -1 to 1. And so it's center, up, middle, down, center. Okay, so this is a sine function and the interval from 0 to 2 pi. And then let's try to locate any relative extrema on this interval. Do you see any relative maximum? So where is it?
Pi over 2.
At pi over 2. So right here, we have a relative max. And do we have any relative minimum?
3 pi over 2.
3 pi over 2. So it's a relative minimum at 3 pi over 2. Everybody okay with this? So now let's find the derivative. What's the derivative of the function? What's f prime?
Cosine.
Prime is cosine. So let's do f prime of pi over 2. What is this? That's cosine of pi over 2. What's cosine of pi over 2? 0. And f prime of 3 pi over 2. That would be cosine of 3 pi over 2. What is this?
0.
What is it? 0, right? So here, that's all what we were saying before, okay? And the point is that this is going to happen, okay? If the function is differentiable at the relative extrema, then the derivative will be 0. Okay, so if there is a derivative, it will be 0. But it could be that there is no derivative. In other words, there is undefined. So if you just look at the zeros of the derivative, you're going to be missing information. You're going to miss those points at which the derivative is not defined. So when you look for relative extrema, your candidates are going to be derivative equal to 0, derivative undefined. Okay? Now, this is not everything. We need to talk about more because let me give you an example. See, how about this? F of x equals x cubed. We know how it looks. This is x cubed. Does it have any relative extrema? Relative max or min? Where?
X equals 0 would be the relative.
So here at 0, remember, to be a relative minimum, for example, means that if I, on an interval around the point 0, this has to be the lowest point. That's not the case.
No.
So, because you see the left part, any interval that you draw, the 0 has to be inside. Any interval that you draw, there is this little part that goes down. Yes? And similarly, there is no maximum because any interval that you draw, then this part, the right part is going to go up. It will be higher than 0. So these have no maximum, no minimum, so no relative extrema. No relative extrema. But, what's the derivative of x cubed? 3x squared. So, what do we know about f prime of 0? What is this equal to? To 0. But this guy is not a relative extrema. So, in other words, what this is telling us is that it doesn't mean that if the derivative is 0, then it will be a relative extrema. No. What we are saying is, if there is a relative extrema, then the derivative may either be 0 or undefined. That's a theorem that we're going to write down. Okay? It's like that statement about if it's continuous, it doesn't have to be differential. But if it is differential, then it has to be continuous. And again, some of you were getting this incorrectly. One of you told me that the two statements mean the same thing. That were the same statement. No, they're not the same thing. If A implies B, that's different than saying B implies A. Okay? So the statement that we're about to write down is that if a point C is a relative extrema, then the derivative is either 0 or undefined at that point. That's not telling you that if the derivative is 0 or undefined, then you have a relative extrema. That's not telling you that. Okay? But the other way around. But that gives you a way of finding candidates. So we need to find a way of detecting cases like these that are not good. Okay? But for that, we need to talk about monotony. All right. So hopefully you understand that these points at which the derivative is undefined or 0 are kind of special because they will allow you to locate this relative extrema, if you will. So we give them a name. Those are called critical points. Okay? So given a function, the critical points or critical numbers of a function are the points at which the derivative is either 0 or undefined. So when you want to locate relative extrema, your first task is find the critical points of the function. Okay? Because those are your candidates. So let me write that down. So critical points. So suppose it is important to be a critical point, the function has to be defined at that point. So it has to be part of the domain. Like for example, absolute value at 0 is defined. If the derivative is not defined, that's okay, but the function itself has to be defined. So let f be defined at x equals c. If the derivative of the function at c equals 0 or is undefined, so if f prime of c is equal to 0 or f prime of c is undefined, then c is called, I like to say critical point. In many places you will see critical point, but technically it's not a point, it's a number. The point would be c comma f of c, okay? But typically we say critical point, but then you could say critical number of the function f, okay? And the motivation for this is because it appeared from our explorations that, if you have a relative extrema, one of these two cases are going to happen, okay? So if you're looking for relative extrema, the place to look for is at points at which this happens. Either the derivative vanish, we call these stationary points. A critical point is called stationary if this is the condition, let me actually say, or undefined, okay? So remark, if f prime of c is equal to 0, then it's a critical point. Then the critical point x equals c is called a stationary point. That's to differentiate it from the undefined part. It's also called the stationary point of f. I'm not going to be using this language, but if you read outside sources, you may find this language. Okay, so when they say a stationary point of a function, that's a point, that's a critical point, but what? The one that gives you 0 in the derivative, not the one that is undefined. Okay, because critical points, they have two natures. Either the derivative vanishes, so it equals 0, or it's undefined. When it vanishes, we give it another name before it's stationary as well. Okay. So we don't have to be saying, oh, the derivative is equal to 0. So just say this and then it implies that. So when you read, that may come across your reading. If you read. Okay, so we have this, so now let's do some examples in finding critical points, and then let's write down the theorem, and let's argue that indeed, if you have a relative extrema, then that point better be a critical number. Okay, and now we're sure that this would be our candidates. But let's first practice how to find critical points. Which basically, let's practice how to solve equations, right? You're going to be solving equations, because to find critical points, what do? Find the derivative, and then you need to either figure out when the function is undefined, so domain of the derivative, and when the derivative equals 0, right? So Finding critical points is a question about domain and solving equations. All right, so examples. Find the critical points of f. And let's see, I'm gonna write some functions here, and the idea here is that the algebra will be slightly different in each of these examples. So let's look at a cubic, then let's look at a radical function. Remember, when you have powers that are fractions, those are really radicals. And then let's look at ln. And let's also practice the sign. Okay, so we want to find the critical points of the function f. So let's do this one by one. Okay. So let's see again. Steps. I mean, it should be clear from the definition, but let me write it. So steps to find critical points. So what's step number one? So find f prime. Step number two.
We graph it.
No graph. No graphing here. Step number two. Find points. Find points on the domain of f for which f prime is undefined. But this is important. It has to be the point has to be in the domain of f, because f prime may be undefined at some places, but if the function f itself is also undefined, then we don't care about those guys, because these are points that are on the graph of f. Okay, so f has to be okay with those points. So find points in the domain of f for which prime is undefined. Then step number three, solve the equation f prime equals 0. Okay. So the critical points are those found, if any, on steps 2 and 3. Okay, maybe that one of these steps doesn't give you anything, or maybe none of them will give you anything. Okay, but if there are any, then they are found on those steps. The reason why I chose this order is because what do you think usually happens with students? Usually students do this. For some reason, this is easy to remember, but you skip this, and then you miss a lot of points. So make sure that you make an effort to stress the fact that you also have to figure out where the derivative is undefined. Because typically this is a condition that's skipped by students, and then you get the problem wrong because you miss points. You don't see all the points, so you could miss a relative extreme. All right, so solution. So let's solve the above questions. So for the first one, let's do the cubic. So we have f of x equals x cubed minus 3x plus 1. So let's find the critical point. So step number one, we find the derivative.
3x squared.
So that's 3x squared minus 3. Okay? Now, here is an advice. Since we need to find zeros and all of that, the first thing, if you get a polynomial or a rational function, factor everything, because it's going to allow you to do the problem easier later on. Okay? So once you find the derivative, then factor as much as you can. In this case, we can do that. So it would be 3 times x squared minus 1. Then this is x plus 1, x minus 1. Okay, so now we have the derivative factor, so then we are ready to read out the information. So the first thing is we need to figure out when the derivative is undefined. So f prime undefined. And then let's figure out when f prime equals 0. So when is the derivative undefined? Is the derivative undefined anywhere? As a polynomial, the domain of this is all real numbers, so there is no problem with this, right? So that's defined everywhere, so none. So we're not gonna get any critical number from here, but then when is f prime equal to 0? So that means 3 times x plus 1, x minus 1 equals 0. And we certainly have solutions here. What are they?
-1 and 1.
So x equals -1, x equals 1. So we found two values at which the derivative is equal to 0. Therefore, we have two critical numbers. Okay? Critical numbers or points. So critical points are x equals -1, x equals 1. So once we write down the theorem, if this function is going to have any relative extrema, it's going to be at these points. Okay? Not at any other. Now, maybe one of them may not be a relative extrema, but if there is any relative extrema, it happens here. So it gives you candidates. Okay, questions? All right. Now, try number 2. The algebra in number 2 is more interesting, but I want you to try first, and then we do it together. So find the critical points for this function. For example, after our discussion in this lecture, in this unit, maybe 1 or 2 lectures down the line, you will be able to take something like this and graph it. Okay? This is something that with pre-calculus alone you cannot do. Okay? And now with the information that we're going to learn, we'll be able to sketch stuff like this. Joshua Acevedo, Eddie Acosta, Brian Arango, Marcos Bucarito, Oscar Camejo, Shavon Campbell, Cassandra Castellón, Carlos Concepción, Diego Concha, Darío de la Nuez, Ulises del Pino, Lester Fernández, Violeta González, Jorge Guntín, Cecilia Izquierdo, Janine Yaurado, Isabela López, Robert López, Cristín Matos, Giovanni Maya, Pilar MacLeod, Ashley Medina, Javier Méndez, Carlos Molina, Alejandro Morales, Macy Reyes, Kyla Ribeiro, Rebeca Romero, Cáceres Tapia, Víctor Torres, Briana Valencia, Fabricio Viña, Mohamed Zia, So I didn't write it down in the steps, but it goes without saying. It's kind of implied here in step number 2. What should be step 0? What should be step 0 in here? So what am I saying here? I'm looking for critical numbers. Where are critical numbers? They must be on the graph, so they are part of the domain. So step 0 is find the domain of the function. Okay, so you need to understand what are the values that you are allowed to consider. So if there is anything that you cannot consider from the beginning, you already have that out of your mind. Okay, so you don't have to worry about those. So even if it's not written here, it's understood that you need to find the domain of the function, so you understand what your pool of possibilities are for critical numbers. So to do this, the first thing is to figure out the domain. So what's the domain of this? Do you know what domain is? Good values for x, so stuff that you're allowed to plug in. So when you find it, what you need to ask yourself is like kind of the opposite question. Is there anything bad? I mean, could anything go wrong here? Is there any problem with this function? Now, when you have fractions, the problem is the bottom could be 0, right? And when you have a square root, the problem is the stuff inside could be negative. Now, here, a potential issue could be because these are radicals, right? But what's the index of these radicals? Remember, the denominator is the index. What's the index? These are cube roots. Is there a problem with cube roots? There's no issue with cube roots. You can do cube root of positive or negative numbers. Do you understand this? So domain here is all real numbers. You can plug in whatever you want and you will get an output. Now, if this would have been a 5/4, that's a different story. Because then this would be a 4th root. That's an even index, so x must be positive or 0. So not negative. Okay? Then you have some restrictions in there. But here, domain is all real numbers. So, anything goes. But you always need to have in mind the domain of the function. And remember, later we want to graph. So the first step is find the domain. So you know what portion of the x-axis will be covered by your graph, etc., etc. So domain is all real numbers. Anybody has an answer for this? X equals -2. So for critical numbers. So critical numbers.
And all numbers from negative to 0.
That many numbers? Really? Interesting. Shouldn't be, but okay. So you mean, what is it? From -3 to 0? This? Like that?
Why put a square in 0?
Bracket. Like that. So any negative number, you mean? It's a critical number. Okay, so we'll see. We'll figure it out. But then why did you say -2? -2 is in there, right?
Oh.
I'm just curious where did you get? I mean, how can you get an interval from an equation? That's
Because they have something over 0, like over 0.
uh-huh.
So you said when it's not defined in derivative.
Okay, so we'll work it out. Okay, good. But let's see. All right, anybody have something else? So typically critical numbers are just a bunch of like 2, 3, 4, 5, but just a finite number of numbers. Okay? So if you get something like this, there's something going on. Okay? So you need to go back and revisit what you did. But we will see it now. All right, let's try to find it. What's the first step? We already know domains are real numbers, so anything goes. Okay? So what's the first thing that we should do? Derivative. So let's find its prime. So power rule all the time. So that will be 3 times 5/3x. Now 5/3 minus 1 is 2/3. Yes. Then minus 15 times 2/3x. Now 2/3 minus 1. That's -1/3. Everybody okay? All right. So now, the idea is let's prepare this so that we can do computations with this. So I'm going to work with this function now. So these 3's cancel out. So we have 5 x to the 2/3 minus, then this is 5, so we get 10. Now this is x to the negative 1 over 3. Negative exponents are misleading. Because when you have a negative exponent, that really means that that guy is in the denominator. So 0 is not good for that expression. Do you understand this? But if you see it there, you may be misled to think that 0 is okay. So if you see a negative exponent, get rid of it immediately. So I'm going to put it down here. Okay? By bringing the expression down. Do you understand this? Next, I'm going to subtract these two guys. So the LCD here is x to the 1/3. And so, you just have to multiply this by x to the 1/3. What's x to the 2/3 times x to the 1/3? Add the exponents. What's 2 over 3 plus 1 over 3? 1. So just x, right? So it's going to be 5x minus 10. Questions? Do you understand how I got this expression? Yes? Okay, so as a derivative, and now this is a very comfortable expression to analyze. So next we need to figure out where f prime is undefined. And also we need to worry about when f prime is equal to 0. So let's see, remember, f prime of x is 5x minus 10 over x to the 1/3. Is this expression undefined at some point? Okay, we have it right there. So let's just look at it. Is it undefined somewhere? Look at the expression. Is it undefined somewhere?
Yeah.
What is it? A 0, right? You cannot plug in 0 there. Anything else is fine. Do you understand? But 0 is a problem. So this is undefined at x equals 0. In other words, to figure out when it's undefined, because it's a fraction, you immediately wonder when the denominator is equal to 0, and by cubing both sides, this will give you x equals 0. Okay? And 0 is part of the domain of the function, because the function is defined everywhere. So this guy is a critical number. Do you understand this? Now, let's go to, and that's it. This is the only place in which the derivative is undefined. Now let's go to the other one, f prime equal to 0. So we need to solve this equation. Now remember, whenever you have a fraction equal to 0, that means the top must be 0, right? The only way that a fraction can be 0 is when the top equals 0. You understand this? Or just move this guy over here, 0 times x to the 1 over 3 is just 0. So this means 5x minus 10 is 0. So what is x? So x is 2. Again, part of the domain. But we have, so I'm just interested, where did that interval come from? Where did you get an interval?
I messed up on algebra.
Okay, so you have to be careful when you do the, if you manage to get here, then remember, get rid of the negative exponent, so you will get something like this. Are you guys comfortable combining things like this? Remember, just make the denominators the same. Here you just need an x to the 1 over 3, so multiply top and bottom by that. Okay? And when you multiply x to the 2/3 times x to the 1 over 3, you add the exponent, 2 over 3 plus 1 over 3 is 3 over 3, which is 1. Okay? That's why it's 5x. And then you activate this process. Okay, so be careful. All right, so we found two critical numbers. So critical numbers, x equals 0 and x equals 2. So once again, I repeat, if this function is going to have any relative extrema, it will happen at any of these two locations. Okay? All right, questions? So x equals 0 is because it's undefined. How do we call this one?
Stationary.
Stationary. They are both critical numbers, but this one is stationary because this one came from f prime being equal to 0. Okay? All right, good. So that will be the first step of many steps that you will do later when you're analyzing a function. But always you want to, one of the steps would be find the critical numbers. Okay? Because those are important values for the function. Are you okay? All right, so now let's analyze. Sometimes you have to do another type of analysis. Well, not always. In this case, it doesn't have to be. So let's see, ln of x. All right, so what's the domain? Here it's very important to look at the domain. What's the domain?
0
Should I include 0? You don't include 0. So 0 to infinity. Remember, ln of 0 is not defined. The argument of ln has to be positive. So if we're looking for any number, any critical number, it has to be positive. Okay? If you get anything that's negative or 0, we don't care about it. All right? Okay, now we activate the process. F prime, what is it? 1 over x. Okay. Now we figure out S prime undefined. F prime equals 0. When is the derivative undefined? So it's undefined at x equals 0. Should we consider this a critical number? What did I just say about domain? What's the domain? 0 to infinity. We don't care about 0. We are only concerned about positive numbers now. Do you understand this? What we actually have is a vertical asymptote at 0. So there's not going to be any critical number there. So this guy is not a critical number since x equals 0 is not in the domain. Remember, the function has to be defined at the point. Okay? Our function is not defined at the point, so we don't care about it. Okay, so, and that's it. There's no other value that makes it undefined, so let's move on to the other one. F prime equal to 0. We need to figure out this equation, 1 over x equals 0. What happens here? There's no solution, right? So no solution, so we don't get anything from here. In other words, this function has no critical numbers. So this example is to show you that there could be functions that have no critical numbers. Okay? Doesn't mean that every function has critical numbers. So f of x equals ln of x has no critical points. Do you understand this? No critical points because we didn't find any. All right, and then I guess to have a trig example, we have the sine of x. All right, let's make it more interesting. So we'll do sine of 2x. Let me change it up here. Let's do sine of 2x. All right. So for this function, the domain is all real numbers, right? So nothing to worry about. So anything goes here. So then we find the derivative. Who can tell me what's the derivative?
2 times cosine 2x.
Very good. So cosine of 2x times 2. Many of you were not putting the times 2 in that little problem that you need to find the second derivative. This is chain rule. Okay? There is a composition here. So the outside function is sine, the inside function is 2x. So if you take the derivative, you do the derivative of the outside, plug in the inside function, and then times the derivative of the inside, which is 2. Many of you were missing these times 2 in that little equation, and then of course the problem is wrong, because then everything else goes down here. All right, so these are derivatives. So now let's see. F prime undefined. F prime equals 0. Is the derivative undefined at any point? That's a cosine function. Cosine function, you know, a very nice function. It's just like the sine function. So none. The cosine is defined everywhere. Does everybody understand this? You can do cosine of whatever you want. Okay? If it was tangent, that's a different story. You actually have to find when cosine is 0, and then that's when tangent is undefined. So, but you get a tangent here, maybe there was a tangent already in the original function or a secant, that then when you take the derivative give you a tangent. And in those cases, for example, if it's a secant up here, then cosine is in the denominator, so those values like cosine is 0, they're not in the domain to begin with. So you don't have to worry about those down here, okay? So remember, we always look for values that are already in the domain of the original function. So here there is none that makes it undefined, so now we need to solve this equation. Let's figure out when the derivative is equal to 0. Here, as you know, we do have some solutions. So that 2 is irrelevant, so that cosine of 2x equals 0. And then we need to solve this equation. Now remember, how do we do this? You just have to figure out when this guy is equal to 0. And as you know, cosine is 0, where? Pi over 2, 3 pi over 2. And we can combine those two by saying pi over 2 plus k pi. Do you remember this? We have discussed this several times already. So that means that the stuff inside, which is 2x, is pi over 2 or pi over 2 plus k pi, where k is an integer. So it's either a pi over 2 or a coterminal to it, or a 3 pi over 2 or a coterminal to it. And the way to package all of that together is by writing this down. And therefore, what is x? We divide by 2. So x is pi over 4 plus k pi over 2. Okay? So we actually have infinitely many critical numbers now. Okay? I guess what I said before about having just a few finitely many, that's only true if your function is not periodic. But if you have a periodic function like the trigonometric functions, if you have a critical number, then any coterminal to it will give you a critical number as well. So you're going to have infinitely many already. Okay? So these are our critical numbers. So if this function is going to have any relative extrema, it's going to be at this point. Okay? All right. Any questions on how to find critical numbers? All right. So now that we understand the procedure, then let's talk about the theorem that we have been mentioning all along. Why are we interested in this? Well, because these are the candidates to find relative extrema. Okay. So let me write it, and then let's argue it, because it's actually nice. It's interesting to see. We have to think about limits again, what we discussed at the very beginning, and it's good to see how those ideas come into play in this stuff that we're doing. Remember, everything is for a reason. I mean, the importance of limits should be already understood, because derivative is a limit. So without limits, we wouldn't have derivatives. So, and now without derivatives, we wouldn't be able to analyze functions. You know, is everything is related. Okay, so theorem. And here is the theorem. So suppose that f has a relative extrema. So this is about relative extrema and critical numbers and critical points. That's what this theorem is about. So suppose, or if f of x has a relative extrema, that means has a relative maximum or relative minimum. So the word extrema is plural for any of these two situations. Okay, so relative extrema. So if f of x has a relative maximum or relative minimum at x equals c, then x equals c is a critical point of f. Okay? Which is the one that we have been saying all along. So if the function has any relative extrema, then that point at which the relative extrema occurs is going to be a critical point. In other words, the derivative is either undefined or is equal to 0. Okay? One of the two things must happen. So let's argue this. I repeat, this is not saying the converse of this is not necessarily true. In fact, it's not true. We have a counter example. Think about the cubic. Okay, the y equals x cubed at x equals 0. That's a critical point, right? Because the derivative vanishes. It's stationary at x equals 0, but that's neither a maximum nor a minimum. Do you understand what I'm saying? So the converse here is not true. The converse of this statement is if x equals c is a critical point, then x equals c, then the function has a relative extrema at x equals c. No, that's not true. Think about x equal cube, y equal x cube. Okay, that's not true. Now what we're saying is the other way around. If we have a relative extrema, then at that point we need to have a critical point. In other words, the derivative either is 0 or undefined. So let's prove that. So proof. So the way the proof is going to go is by contradiction. Okay. So what do I mean by this? Sometimes when we want to argue something, let's say that you want to argue a certain statement, sometimes it's helpful, it's beneficial to actually assume the opposite of what you want. Okay. So assume the opposite of what you want, and then starting with that assumption, you start working and doing a bunch of logical steps. If eventually you get to something that doesn't make sense, something that's not true, that means that something went wrong along the way. If you trust all the steps that you did, then the only thing that could have been wrong is your original assumption. Now, you assume that the opposite was true. That's wrong. So what must be true is the opposite of the opposite, which is what you want. Okay? That's how proof by contradiction works. Like, for example, I'm not going to go super into details, but how do you prove that there are infinitely many primes? For example, do you agree that there are infinitely many prime numbers? Why? How do you know that there are infinitely many primes? In fact, the density of the primes is not known. Like at the beginning, the primes are very next to each other, but then when you start looking for bigger, when you have bigger and bigger numbers, then the primes start to scatter more and more, and it's actually very difficult to find big primes. In fact, whoever holds the largest non-prime has the power of cryptography, because most of all the cryptographic algorithms and so on, they are based on the fact that finding large prime numbers is very difficult, and in general, factoring very big numbers is difficult, okay? Because you need to find large primes, and this is difficult. So if you have the largest prime in your hand, no, because the point is that there is no largest, there are infinitely many. But there is, there is a largest known prime. If you have it, then you have the power at that point, until somebody else finds something else. But how do we know that there are infinitely many? Here is a very simple argument. By contradiction. Again, I'm not going to go super into detail, but just to give you an idea, the point is, well, suppose the opposite. What would be the opposite? That there are finitely many. So suppose that we have finitely many. So there are n primes. All the primes, there are n of them. Let's call them P1, P2, all the way up to Pn. These are all the primes. Okay? For some n. Maybe this n is a million, whatever. But there are only finitely many. Suppose this. Okay, then here's what I'm going to do. Let us consider the following number. So consider the number, I don't know, I'm going to call it m. It's going to be the product of all of these guys plus 1. This is a natural number, right? It's a number. I can multiply all of these numbers and do plus 1. So that's a number. I claim that none of these numbers divide this one. Now, a theorem means that if a number is not prime, so first of all, this is not prime, right? Why is this not prime? Well, it's not divisible by all the other ones. But why it is not prime? Because we have all the primes here. Right? Remember, we assume that these are all the primes. And definitely this guy is none of these. Because I just multiplied them all and did plus 1. Do you understand this? So this is definitely not a prime number, because if it were, it would be in this list. Do you understand this? So it's not a prime number. But Pi does not divide M for all I. In other words, none of these guys divide this number. Why? Because I'm going to use P1. But the same thing that I do for P1 will be for P2, for P3, whatever prime in here. So if P1 divides M, this is the symbol for divide. If P1 divides M, then that means that P1 divides P1 times Pn plus 1. Now, if P1 divides the sum, that means that if it divides the sum, and because it divides one of the terms in the sum, it better divide the other one, okay? Because P1 divides P1 times Pn, then because it divides the whole sum, it has to divide 1. For example, 3 divides 6 plus 5. No, this is actually what's happening. So 3 divides 6 plus 9, which is 15, right? And well, because it divides 6 and it divides 9, therefore it divides 6 plus 9. Now, if we say, now we cannot say that 3 divides 6 plus 5. Why? Because even though it divides 6, it has to divide 5 and it doesn't. Remember, this is 11. This is not true. Okay? And this is the kind of situation that we have here. So, none of the primes divide m, because if they do, then they divide an expression like this. Because they divide one of the summands, they will have to divide the other guy as well. But if P1 divides 1, that means that P1 is equal to 1. But by definition, 1 is not a prime number. The prime number is a number that's different than 1 and is only divisible by itself and 1. Okay? But 1 doesn't count as a prime number. And this is a contradiction right here. So P1 cannot divide. I'm doing P1. P1 cannot divide m, but the same argument that I did here, I can do it with P2, with P3, with P4, with Pn. So none of these guys, that's what I mean by this line, none of the pi's divide this number. But then that means this is prime, because we have a theorem that says that every number that's not prime has to be divisible by some prime. Otherwise, it would be prime. Right? So that's a contradiction. We said that it's not prime, but then we're getting here that it has to be a prime because it's not divided by anybody. None of the primes are winning. So that's the problem. What is the whole problem? That we said that they were finitely many, so there has to be infinitely many. Okay? This proof is due to Euclid's, back from the Greeks. From the Greeks, this is how he proved that there are infinitely many primes. Okay? If you like this kind of argument, try to do this. Square root of 2 is an irrational number. Prove it. So prove that square root of 2 is irrational. In other words, that means it's not a rational number. So in other words, the square root of 2 cannot be written as a fraction. P over Q, where P and Q are integers. That's what it means to say that a number is irrational. It cannot be written as a fraction. To argue this, you do it by contradiction. Assume that it can be written as a fraction, and then you work from there. Okay? If you take discrete, you learn this kind of stuff. If you take discrete math. I'm teaching in the fall. But that's an interesting class, depending who teaches. Okay, anyways. So this is what we're going to do. We're going to do a proof by contradiction, but it's going to be way simpler than this, because here this is using, I mean, this is simple. This is simple if you know all of these little facts about number theory. Okay? That's it. But just to give you, this was just to give you an example of how proof by contradiction works. So we're going to use it here. Okay? You will see how. So if f of x has a relative maximum or relative minimum at x equals c, then x equals c is a critical point of f. Okay, so this is an if-then statement. How do you argue if-then? You assume the if part, and then you want to prove with that information, you want to prove the then part. Okay, so this is your hypothesis. So you take it for granted. So let x equals c be a relative extreme. It could be maximum or minimum. I don't know what it is. Okay, be a relative extrema of f. Now, there are two cases. Okay. Either the derivative of f is defined as c or not. If it's not defined, we're done, because then we satisfy one of the conditions of critical point. So what's interesting to see is what happens if it is defined. If it is defined, we need to argue that it's better be c. Right? That's what we need to do. So if f prime of c is undefined, then we're done. Then that means that we have a critical number in our hands, right? So the question is, okay, what if it is defined? So assume f prime of c is defined. Okay? Because if it's undefined, we're done. We already have a critical number because of one of the conditions. Now, what if it's defined? I want to show that this number must be c. Okay? All we know is that c is a relative extrema. I want to know that this number is c. So what I'm going to do is, I'm going to argue that if we say, because this number is either 0, positive, or negative. If we say that it's positive, then that will violate the relative extrema condition. So we get a contradiction, so it cannot be positive. Similarly, if we say that it's negative, it will violate the extrema condition. So the only condition that's left is that it's better visible. Okay, that's how the argument is going to go. So assume f prime of c is defined. So this is a number. So then it is either positive, negative, or 0. I mean, if you pick any number whatsoever, those are the 3 possibilities for any number that you pick. Let's argue that the first 2 are not possible. So case 1. Let's say that this was positive. Okay? So if the derivative at c is positive, then what do we have from here? Well, let's use the definition. So what do we know about f prime of c? This is the limit as x approaches c, f of x minus f of c of x minus c. Right? The tentative definition of derivative. Part B of the first question in test 2. Yes? That's the tentative definition of derivative. So we are saying that this is a positive number. Now let's think about what we're saying here. So we're saying that this limit is positive. Now remember, what is a limit? What is that we're saying? This right here is a function, right? This difference, this fraction here, this is a function. And we're saying that when x is very close to c, the values of this function are closer and closer to some positive number. Do you understand this? In particular, if you are very close to c, this function itself, without the limit, it has to be positive. Because if this function is always negative, then there's no way that you can get close to something positive. Do you understand what I'm saying? So by using the notion of limit, it follows then, so for x close enough to c, the function itself without the limit expression is positive. Do you understand this? Do you understand this? Remember, this means that this function, whatever it is getting close to some positive number when x is close to c. To get close to something positive, eventually you have to be positive itself. Okay? Otherwise, if you are always negative, how can you get close to something positive? You need to go to 0 at some point. Because if it's differential, it has to be continuous, so there's no jumping, nothing weird happening. Does that make sense?
Yes.
Okay. So, now let's look at this. What does this mean? We have a fraction that's positive. What does this mean about the top and the bottom? Or both are negative. So from here we get that top and bottom, they better have the same sign. Yes? So from this condition, we get that both the top and the bottom have the same sign. Okay? All right. Again, I'm not doing this not because I'm going to ask you for this on the exam, just to show you that mathematics is a little bit different than just moving things around and solving equations and that kind of stuff. Okay? It's more than that. It's about ideas. So we're doing it. Okay? We're playing with the concepts that we have discussed so far. So this means that both, and stuff you know from before. So it means that both top and bottom have the same sign. Okay. So now, remember, this is happening around C, right? We're getting close enough to C. Let's see what happens if we were doing it from the left or from the right. Because if this limit exists, it's a two-sided limit, right? Right and left, we need to have the same behavior. It has to go towards the same place. Okay? So if x is less than c, so here we're getting close to c from the left, yes? If x is less than c, then what can you say about x minus c? It's negative, right? If x is less than c, just move the c over here. X minus c is negative. Therefore, what can you say about f of x minus f of c? It's negative because they have the same sign, which means then that f of x is less than f of c. Do you understand this? What does this imply about f of c? Remember, this is happening around c, so this is inside a little interval. This is happening to the left of c. So to the left of C, f of x is less than f of c. So this guy cannot be a relative minimum. It could still be a maximum, but it cannot be a minimum because we found stuff that is less than that. To the left. Do you understand this? Close to it, to the left, we found stuff that is less than that. So this means that it cannot be a minimum. So f of c cannot be a relative minimum. Okay, that's fine, but maybe it's a maximum, okay? So far this argument is telling us that it cannot be a minimum in this condition, all right? Let's look at what happens to the right. This was just from the left, okay? So what happens if we are around C, but from the right? So if x is bigger than C, so close, but bigger than C, then x minus C is positive, which would tell us that f of x minus f of c is positive, which then tells us that f of x is bigger than f of c. And now what is this inequality telling us? Can f of c be a relative max? No, because we found stuff next to it that are bigger than that, okay? So the closer you are, the more these inequalities are true. So there's no way it can be a relative max. So f of c cannot be a relative max. But this right here is a problem because we started by saying that f of c was a relative extrema, right? So we're saying here that f of c is not a relative extrema then. If not a relative extrema, and this is a contradiction because this contradicts our assumption that assumption is untouchable. You cannot touch this one, that f of c is a relative extrema because that's our hypothesis. Okay, you cannot touch that one. Now, what that means is, because we got a contradiction, it means that this case is impossible to have. There's no way that you can have a positive derivative at C. If you have a positive derivative, then those problems show up, and then you cannot have a relative extreme. So the other cases that are left is, okay, then this number is either negative or 0. The point is that when it's negative, you play a similar game. If it's negative, then it means that this function itself has to be negative when you're close enough. When a fraction is negative, that means top and bottom have different signs. And then you play the same game, and then from either side, you're going to get violation of. And from one side, you will get that it's no longer a relative maximum. From the other one, you get no longer a relative minimum. So that will also give you an issue, just like what was happening here. So then the only possibility that is left is that then it has to be 0. Okay? So that's how the statement works. So I'm just going to say case 2. So let me say, so f prime of c cannot be positive. Okay, so case 2, okay, maybe it's negative. Then the thing is that here, similarly, so similarly, by this I mean just a similar argument to case 1. Similarly, just like in case 1, we get a contradiction here. So f prime of c cannot be negative. Therefore, the only possibility for it, because we said that it was defined, then it's a number, it has to be 0. Okay? So if you want, try to do case number 2 on your own. Okay? Again, it's exactly the same idea that we did above, literally the same. It's just that instead of greater than, it will be less than 0. So here, you have to say that this is negative, and then just switch around in this statement. Instead of saying they have to have the same sign, they have to have opposite sign. Because a fraction negative means one has to be positive, the other one has to be negative. Okay? Doesn't matter which one it is, but they have opposite sign, and then you play the same thing. For example, here, if this was negative, then you will get that this will have to be positive, and then what will be violated would be the maximum condition. And then when this is positive, then this is negative, and then what's violated is the minimum condition. Right? At the end of the day, both conditions are violated. That's why in math, when this happens, we say similarly because there's no need to repeat the same thing. Okay, so moral of the story. If you're going to look for relative extrema, now we know for sure that if you have a relative extrema, then it has to be a critical point. So now when I ask you to find relative extrema of a function, we still need a tool to find them. But the candidates are here, okay? Are critical points. Okay. Oh, I thought we were until 11:20. Never mind. I know we're done. It's just that I have another class Tuesday and Thursday that is until 11:20, and I thought that we had to do that. That's okay. Yes. I have the exams here, so you can pick them up before you leave. So up to where?
All the way down